So here's what I made up earlier. So when we talk about projective space, I want to start from the three-dimensional space. So like the space we live in the world. So three dimensions, so x, y, and z. And here's a cone. Okay, cone. No, not cone. Cone surface. It's not an object. It's just a surface. So this surface exists in a three-dimensional space. It's not accuracy, but just dimension. And now, so what's the difference for the P2? So the projective space P2 and the three-dimensional real number space. So there's two differences. First difference, we remove the original point. We remove the original point. So So the three-dimensional space x, y, and z. So the first difference is we remove the original point. So we remove the 0, 0, 0. And the second and the second thing is we see on the surface. Like if here we found the original point, we have a bunch of vectors, right? Each one is vector. You have the directions. So no matter how long the vector it is, they're always the same vector. So like from here, so if I cut it in half, so like from here. So vector with this long and with this long, they are also the same vector. They are same. So that's why we mentioned. So we want to like A, B, C over K. I think that's right? I forgot the form, but yeah. So we just get rid of the distance or the length, the difference of the length. So that's a big thing. So now, I draw a plane. This is x, and this is y. And here we have z. Okay? We have z. And I put the cone like this. And now, because and now I can cut this shape, right? So I use a plane is parallel to this part. And I cut it. And then you can find the circle inside. You can find the circle inside. Yeah, because I cut it, right? Cut it by a plane which is vertical to the z rays. We can have different circles with the different sides. But for this feature, for the feature I mentioned, the second feature, all those circles are actually the same one. Right? Yeah. Anyone follows?
The vertical, the circle is always the same no matter where you cut, basically.
Yeah. Whatever the size is, because we got rid of the size. Yeah. So and let me think. Okay. And the second thing is because okay. Yeah. Let me write down the equation. So for this shape, we have x squared plus y squared equals to z squared, right? And we will want to have a circle, so a little bit magic or trick. So we can have this, like if we want like z equals to 0, so we have right? So we have this. And because of the second feature, so no matter how big the J is, so we don't care about that. So now, because of the feature 2, we can get rid of J. So we have this one. Right? It's a circle. Right? It's a circle on the 2-dimensional space, right? A surface. Yeah. So we get this one, right? But the key thing is here. So we cannot let Z equals to 0. Yeah, because when we let Z equals to 0, so imagine we have the knife, we cut the shape. We cut the shape without, we cut the shape, like this is the step we cut the shape, right? The Z cannot be equal to 0. So which means this knife cannot be on the plane, right? So it must be, have some distance. If the knife cross on this plane, we cannot satisfy the first two features. Yeah, because there's no 0, 0, 0 in this projective space. Yeah. And why? Because it's this thing have no dimension, have no directions, right? Direction. Yeah. Yeah, because this thing have no direction at the projective space. All the elements have the direction. Yeah. Also, but now I think that's all for the projective space to the affine space. So you just use a knife, and if you want a knife parallel to this plane, so you just like Z. So you just get rid of Z. So if you want to have a knife in this way, so you cut off Y or X, it really depends on you. Yeah, because if you cut this with this shape, with a knife like this, you will get, right? I think in primary school we talked about those before. High school. Sorry, so my English just ignore that, okay? Yeah, my English is primary school level, okay? Sorry, just kidding. Yeah, but whatever. Why it doesn't matter. So yeah, I think that's it. So it's really how you cut. It's just like you cut a shape in a three-dimensional space, actually in the projective space, and you got the surface. You got the result from the 截面怎么说 I don't know. You got the surface. You got the surface. When you cut it, you got the result. Yeah. And yeah, that's it. And when you cut the knife, you cannot the knife be 0. So that's a really interesting way. And now we want to know. So because when we talk about the equilibrium curves or the circle group, sometimes we mention about the infinity space. Infinity point. I'm not quite familiar with the circle group, but I'll show you how to do the calculation. First, we come with a knife, right? The knife is not this plane, but actually, let's back to the projective space. But actually, in this plane, we have the vector like this, right? We have the vector on those plane, right? On this plane, the vector looks like x, y, and 0, right? Which is not on here, right? So in this plane is infinity to this shape. So if it's infinity to this shape, So we want to find maybe if we have a solution, if this plane and this equation have a common solution, so we can define it as the infinity point. Yeah, because you cannot find the vector on this plane on the affine space. Everyone follows? Okay. Yeah. So now how to do the calculation? Okay, yeah. So now that's cut part, right? Now we want to calculate the result with this one and this one. So we let z equals to 0. So like we have x plus y squared equals to z, right? So here we let z equals to 0. And then we have the solution like x equals to 0, y equals to 0, if we do it on the real number, right? So 0, 0, 0, and which means this shape is perfectly projective to the affine space because there is no solution, because 0, 0, 0 is not belongs to the projective space. But if we go on the complex number, so we have 1 minus 1, right? I think we also have negative 1 minus, 1, 1, and 1 I, and 1 minus 1 I. Yeah. So because we put it into the equation, we can find the solution, right? So like. I negative 1 I, right? Then I put 0 inside. Yeah. We can find a solution. So this really depends on which field we're talking about. So which means all the vectors on the surface have the exactly point on the affine space. So this is x squared plus y squared equals to 1. Okay, so everyone follows. Yeah, and now let's talk another example. It's EC curves. So when we read I think when we read some articles like what is an eclipse curve, sorry about my English. So read some articles, we always have a line like this, right? A EC curve is more like a line like this with an infinity point, and the infinity point is not on the plane, right? So, but before we talk about the projective space, so for my personal experience, before I know the projective space, I cannot understand what the heck is infinite point. Now we understand. So now we understand one thing. So when we cut the shape by z, by the plane like this, vector vertical to the z. So each vectors on this plane cannot map into this space. So which means this vector is infinity to this picture. So that's infinity. And because in projective space, actually the vector is a dot, a point, call it a point. So that's infinity point. Right. So now we have the shape like this. So which means we almost like things and go through with the original point. And imagine we also have the knife. We have the knife cut the shape, and we got the shape like this. And back to this step. So what's the formula of the EC curve? I forgot.
It's x cubed plus ax plus b minus y squared.
Easy one.
Y squared
Y squared
equals to x
triple
cube plus ax plus b.
Okay.
Y
Plus b. Okay, so yeah, so we have this, and we have the knife, right? We have the knife, and in here when we talk about the EC curve, we just change the formula. We change the formula from this one to we change to this one, right? from this formula change to this formula, and the rest of things are same. So we just write z equals to 0. Sorry, we should. Okay, the formula actually is z. I have to draw this line. Actually, this is the formula on the affine space. This formula is on the affine space, and this formula, if we get rid of it, this formula is on the affine space. So we want to calculate the infinite point in the projective space. So we must recover this formula to the projective form. So it will go like this. So I'm not going to explain too much. So just give you the equation. So it will be like z squared times equals x squared times a x times z squared times something like this. So this has a 3 degree square 3. This term have degree 3. This term have degree 3. This term degree 3. This term degree 3. So that's a point. Degree. The degree is 6. And now you put this 0 equals to 0. Oh, sorry. Z equals to 0. And put it into this formula, and you calculate the result. And then you will find the result is probably 0, 1, 0. Right? Probably this one. And we define this point as the infinity point to the curve. And that's it. Yeah, that's all. Yeah. No. So, any question or something makes you confusing or okay?
Nice. So I understood that x by z, we basically calculate x as z with the knife.
Yeah.
And then we have also the circle. Then when we talked about the infinity points, you were talking about how if you were painting the vectors from here. And I mean they still hit the.
The vector is specifically on this plane. It's not going like this. It's not. It's like this. Exactly on the plane. Yeah. So that's the point. So yeah, because I cannot draw this really specific.
It's on the plane.
Yeah, on the the plane is z equals to 0.
Yeah.
Yeah.
Okay, got it.
Yeah. Okay.